Hello. Hello.
Hello. Good
Am I
evening, ma'am.
audible?
Yes, ma'am.
Okay. So you tried that spinel questions related to that?
Yes, ma'am.
Okay. We'll start from 7.5. Okay. Okay, so we'll start the class. Good evening, everyone. We were discussing GATE 2018 inorganic chemistry questions. So today we will start with question number 16, that is the symmetry label of valence p orbitals of a metal ion in an octahedral ligand field is option number A T1G, option number B T1U, option number C EG plus A1G, and option number D T2G. Okay. So in this question, they have asked us to write what is the symmetry label for p valence p orbital of a metal ion which is an octahedral field. Now we can do this question by taking, like, it will be easier to visualize if we start with d orbital. Okay, I will tell you how it is coming. So first of all, we know that there are total 5 degenerate d orbitals if it is not in any crystal field, right? 5 degenerate d orbitals are there, which are dxy, dyz, and dxz, and dx square minus y square, and dz square. Okay, and we consider this as xy, then here the d orbital is like this. If this is dyz, this is yz axis, then it yz plane, then it dyz is this. If it's dxz, then this is dx and this is z. Whereas if it is x, sorry, very sorry. Okay. So dxy, dyz and dxz planes are, we know, between the axes, right? So if this is x and y, then the dxy orbital will be present as this. If this is dyz, then if this is yz axis, then dyz will be somewhat like this. If it's xz, then it will be between the axis. Whereas for dx square minus y square, if this is xy plane, then the d orbitals are like this. That is, it will lie along the axis. And for dz square, this is the z axis. Okay. So what happens is that here they are asking about octahedral ligand field. Okay, so in an octahedral ligand field, the ligands come, like they approach from the axis. So if we see these 5 orbitals, then we can see that only dx square minus y square and dz square, for these two for these two d orbitals only, the metal ions d orbital lobes, they are lying along the axis. And in an octahedral field also, if a ligand comes, it approaches through the axis. Therefore there will be repulsion, there will be more repulsion, and we see this splitting, like the 5 degenerate d orbitals, they split into two set, which is eg and t2g, right? eg and t2g. So this t2g, this will consist of dxy, dyz and dxz, whereas eg will consist of dx square minus y square and dz square. So because of more repulsion, this eg is going higher in energy, and we see this type of splitting, this degenerate d orbitals, they split into two energy sets, which are t2g and eg. Now one more thing, why this g is coming, anyone knows this?
Center of symmetry.
Yeah, so if we see here for the all the d orbital lobes, if we see, this is the center of symmetry, like both the sides, if we go, it is plus, right? In both the sides it is plus, so it is having that center of symmetry in all the orbitals, like all the d orbitals in both the sides of the lobes, it is having the same sign. So this is Girardic. Okay, whereas if the symmetry was absent, like if it was plus and minus in one side, then it will be ungirardic. So this g is coming from that, And why this T and E is coming? This T is because it's triply degenerate, because here, like, these orbitals, there are 3 orbitals we can see. So this is triply degenerate, and the EG1 is doubly degenerate. Degenerate. Okay. So from here we have an idea that from where these terms are coming. This TE, if it's triply degenerate, then T term is coming. If it's doubly degenerate, then E term comes. For monodegenerate one, A term comes. And this G and U, this depends on whether center of symmetry that is present or not. If it's present, then it is G. If it's not present, then it is U. Okay. So now we will see what happens for a p orbital. Now we know that in a p orbital lobe, how many p orbitals we have, right? Px, py and pz, right? And all of them, okay, z, x, y. Okay, but here if this side is plus, then this lobe will be minus. So here we can say that, okay, we will go one by one. So now we are having 3 p orbitals, and we know that in octahedral field the ligand approaches from where? From the axis, right? So in this case, as all the 3 orbitals, they are present along the axis only. One is along x-axis, one is along y-axis, and the other one is along z-axis. So all of them are present on the axis, so they will face the repulsion equally and their energy will rise. Okay, so if these are the 3 degenerate p orbitals, then in an octahedral crystal field, what will happen? Their energy will increase, and all the 3 of them, they will face the repulsion, they will face, because of that repulsion between this metal lobes, metal p orbital lobes and the approaching ligand orbital, they will face repulsion, and it will become higher in energy. So but here, since all the 3 of them are present on axis, so it will be a triply degenerate one, right? Because for px, py, pz, in all the 3 cases it's increasing, right? So it is triply degenerate. So from here we can first cancel out this eg and a1g option. Now we have these 3 options remaining: T1G, T1U and T2G. Now, as you already pointed out, this G and U term comes from center of symmetry. So can anyone tell me whether these p orbitals are having center of symmetry or not?
No, ma'am.
Okay, so for this case it will be U, right? And here in the option we can see that the other 2 options are T1G and T2G, whereas only in this B case we can see it is T1U. And this, if you ask for this 1 and 2, from where these 2 things, these 1 or 2 number is coming, so it's coming from group theory. And also I am also not having a clear cut idea of this, but uh, if you want to know, I will go through it and I will come up with this, that why 1 and U, this 2, this term was coming, is coming. But this T and E, A, these are coming for the degeneracy, how much degenerate are the orbitals. And this G and U, they come from center of symmetry. So for this question, that is the symmetry label for valence p orbitals of a metal ion in an octahedral ligand field, the symmetry will be T1U. So is it clear?
Yes, ma'am.
Yeah, it's clear for everyone.
Yes, ma'am.
Okay. we will move on to the next question, which is question number 33 from GATE 2018 chemistry paper. So the question is, the elimination product of the following reaction is. So here one rhodium complex is given, which is like 6 ligands are coordinated to it. So it's an octahedral complex, which this rhodium is coordinated to one CH3, 3I and 2 carbonyl ligands, and this complex is having an overall charge of minus, and the reaction is carbonyl CO is given in 35 bar at 453 Kelvin. What will be the elimination product from this compound? Okay, so first of all, let's this RH CH3I CH3I I and 2 carbonyl ligands. So what is the total number of valence electrons in this complex?
Ma'am, D7?
Yeah, rhodium is D. So from there 7 electrons are coming. It's a D7 stem. Then from CS3 gives how many electrons?
1.
Yeah, and each of the iodine I will give 1 each, and carbonyl is,
2 electron.
yeah, so there are 2 carbonyl ligands and the complex is having an overall charge of minus, so 1 electron will be added. So it's 7 plus 1 plus 3 plus 2 plus 1, so 10, 11, 12, 13, 14.
It
Wait,
is 4. 2 into 2, 4.
oh, sorry. No, why rhodium will be 7? Because here we are counting from neutral method, right? So it will be 9 electrons, right?
9. 9.
It's clear to you. I think Shikha,
Yes, ma'am.
someone, yeah. So it will give, we are counting by neutral method. So 9 from rhodium, 1 from CS3, 1 each from all the iodine, and 2 from each of the carbonyls. So here this is an 18 electron system, and we know that complexes prefer to be in 18 as an 18 electron complex, right? It is more stable in that form. So now when they are giving CO, then what will happen? This complex, since it is coordinate, first of all it is coordinatively unsaturated because it is already coordinated to 6 ligands, and also it is electronically saturated. It is already having 18 electrons, so it's already an 18 electron complex. So in this case what will happen is, first migratory insertion will take place, okay, so that one, like, it will reduce its coordination number and number of electrons, both the things, number of valence electrons, and then this CO will come. So let's write this CO with an other color. So this is the CO. Okay. This is the incoming CO. Then here, first of all, migratory insertion will take place. So when we are having CH3 and CO, these two ligands attached to a metal, then this CH3 can undergo migratory insertion in this carbonyl ligand. I think you all are familiar with that. Okay, so we are having this rhodium complex and I here CO CH3. So this CH3 is getting migrated in this carbonyl ligand CO. This is I, and now this place is vacant, right? So now this is how many electron system?
17.
You said 17. How 17? Rhodium will give 9. 3 from here, so it's 12, 13, 14, 15, and 1 from this minus charge. So it is now a 16 electron complex, not 17. Okay. Because COCH3 is also, like, it also gives 1 electron. Okay, acyl, this is an acyl group. So acyl group, they also gives 1 electron to this metal center. So now we are having this. Now what will happen is this incoming, this CO, which is given in the question, now it will attack and we will get this complex, which is RH OCH3 CO I and this CO. Okay. So this is again an 18 electron complex. But here they are saying that reductive elimination is taking place. And why? Because they are giving this high temperature, 453 Kelvin. So here elimination product they are asking. So from here, now the next step will be reductive elimination. So in reductive elimination, what happens? Yes. And see. So in reductive elimination, what happens? First of all, the number of valence electron that also decreases. If it's an 18 electron complex, so from that it will become an 16 electron complex, and the coordination number also decreases. So one is number of valence electron decreases, coordination number decreases, and also reductive elimination takes place like only if the two ligands are cis to each other. Okay, so it is a necessary condition for reductive elimination. If the ligands are cis, then only this can take place. If they are trans, then it is not prone to reductive elimination. So which ligands are cis to each other? That we have to see. Now coming to the question, the options given are option number A, I2, option number B is CH3I, option number C is CH3COI, and option number D is I3 minus. I2, CH3I, CH3COI, and I3 minus. So two ligands will be coming out, right, after reductive elimination. And yeah, also after reductive elimination, the oxidation state also decreases. So here, this COCH3 and I, they are cis to each other, right? Whereas there is no question of this coming out, and CH3 already got migrated, so CH migrated inside that carbonyl ligand, so CH3I can't be the option, I3 minus also no, and I2 will also not come out just like that. Okay, so in this question, this since this COCH3 and this I, they are cis to each other, so these two will come out. and the elimination product will be CH3 COI. Okay, so for this question, that is the elimination product of the following reaction is CH3COI. So this is the correct option. Is it clear?
Ma'am, repeat the step of reductive elimination.
Reductive elimination. Okay. So reductive elimination means two ligands. Let's say we are having M and AB. This is the ligand. Let's say this. So if this is taking place, MAB 0 plus 2. So if this type of reaction is taking place, we call this oxidative addition. And just the reverse of this is reductive elimination. That is, we are having MAB, and from here AB will come out and will be this metal complex, whatever the other things are remaining. So what happens in reductive elimination is the oxidation state, it decreases. If there are, we can see that here A, B were coordinated, now A, B are coming out together. So the coordination number, that is also decreasing. And as we saw in this case, that earlier it is an 18 electron complex, but if CH3COI will come out, then it will become a 16 electron complex. Okay. So what is happening here also, they are asking that what is the elimination product. So in this case, here we can see why this reductive elimination is taking place, because they are giving high temperature. And so from here, from this complex, after the migratory insertion step, now reductive elimination will take place. So now we have to see that what will come out, like which two ligands will combine and they will come out. So for that also, only the ligands which are present cis to each other, okay, they can come out, right, together, like CH3COI. Okay, if CH3 was there, let's say if this insertion would not have taken place, if we had some CH3 outside also, then there was a possibility that CH3I will also come out. But here it's CH3CO, CH3 and I, these two will come out as they are present cis to each other. I3 minus can't come out, okay, because we are not having anything like that. CH3I also, it can't come out, and I2 will also, we can have this question that why not these two I are coming out, right, because they are also cis to each other. But I2 will also not come out. CH3I will prefer, like it will prefer more to get eliminated than these two iodines. It will not come out like that.
Why? Why? What is the reason behind this?
So actually, I too don't know the exact reason for this, but I feel that this iodine will just, okay, here
Uh,
also,
Ma'am,
yeah.
if you compare the bond distance or bond strength, RH carbonyl bond strength is more than RI bond. I think here I2 is more probable to elimination reactions.
What?
RH and carbonyl bond strength is more than RI bond strength. Here is RH in RH and carbonyl bond having the double bond character, but not RH and I bond. The strength between RH and CO bond strength is a partial double bond character,
Here
but not.
this, yeah, that is so. If you are saying on the basis of this bond strength, right, that
Yeah,
RHCO, this is more preferable.
yes, ma'am.
Actually, I also had this doubt that why not I2, because I2, it is again a gas, so it will, like, I2 will prefer coming out more. So okay,
Ma'am, please hold this question and come with suitable explanation.
what?
Ma'am, please hold this question because I'm also getting doubt why not I too.
Yeah,
That's why I asked to repeat you the reductive elimination part.
Okay, I will see this. Okay, I just I will look into this. Okay, I am telling this afterwards. Let's see. I will try to find out why it is not coming out. Okay, I will read more on this. Anything else like the other three or other two options? That won't be the answers. That's clear, right? Okay. So can I go to the next question? I will look into this question and I will get back.
Yes, ma'am.
Yeah.
Ma'am, is there any role of trans effect in this case?
What?
Trans effect in this case?
What effect? You are not.
Trans effect.
Trans effect, how you are saying, can you explain?
Ma'am, I'm not saying, I'm just asking that is there role of trans effect here?
Well, I am not sure whether trans effect is playing any role here.
Okay, ma'am.
So you are saying that because of this, it's not. Then why? I will see. I will check and I will. Okay. So the next question is question number 36. So in this question, they have asked that what is the spectroscopic ground state term symbols of cobalt ions in COH2O whole 6 whole 2 plus and COCl4 whole 2 minus respectively. So what are the ground state term symbols for these two given complexes? So the two complexes given are cobalt H2O 6 2 plus and cobalt Cl4 2 minus. So first of all, let's find out what is the oxidation state for cobalt in both the two complexes. So if we consider it as X, then X plus water is a neutral ligand and the complex is having an overall charge of 2. So X is equal to plus 2, and in this option or in this complex also, cobalt, if we consider its oxidation state as X, then Cl carries how much charge?
Negative.
So, and the overall charge of the complex is minus 2. So it's X minus 4 is equal to minus 2. That is X is equal to plus 2 again. So for both the complexes, cobalt is in plus 2 oxidation state and cobalt is having free cobalt. It has D7H2 configuration, but since it is in plus 2 oxidation state, so it's a D7 system. Now in one case, there are 6 water ligands and in the other case, there are 4 Cl ligands. So COH2O whole 6, it is an octahedral complex, whereas this COCl4, it is a tetrahedral complex. So now, if we know Orgel diagram, like we should know that Orgel diagram. So what is Orgel diagram? These are correlation diagrams. So you can find these things in this given link. This is given by Professor Debashish Rai from Department of chemistry, you can search Orgel diagram NPTEL and you will get this. So Orgel diagram, these are correlation diagrams which shows the relative energy of electronic terms in transition metal complexes. Orgel diagrams are restricted to only show weak field, that is high spin cases, and offer no information about strong field low spin cases. Because Orgel diagrams are qualitative, no energy calculations can be performed from these diagrams. Also, Orgel diagrams only show the symmetry states of the higher spin multiplicity instead of all the possible terms. And this is the group theory analysis of term splitting. So one day we had discussed that how we find out term symbol for a complex. Okay, so if we are getting S as the term, then the irreducible representation of that in octahedral symmetry will be A1G. If it's P, it's T1G. If it's D, it's EG plus T2G. So actually S means this is 0. So number of states, this will be 2 into 0 plus 1. So it's 1. A1G it's coming. If it's P, then it is 2 into 1 plus 1. That is 3. So T means this triply degenerate. If it's D, then 2 into 2 plus 1. That is 5. And 5, this E, that is 1 doubly degenerate and 1 triply degenerate can make a total of 5. If it's F, then it's 2 into 3 plus 1. That is 6 plus 1, 7. So 7, A means 1, T3 and T2G 3. So these are the 7 states. And then G means like that only it will go on. 2 into 4 plus 1, that is 8 plus 1, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And for H and I also it goes like that. So these things comes from group theory. Okay. So now if we see for these two complexes, that is in both the complexes, cobalt is a D7 system, right? So for a D7 system, let's find out this 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, and 7. So yeah, here cobalt H2O whole 6, 2 plus, and cobalt 4Cl4 ligand and 2 minus. Both like, can anyone tell me water is a weak field ligand or strong field ligand?
Weak
Ma'am,
field ligand, ma'am.
weak field even.
Yeah, so it's a weak field ligand. Also, Cl is a weak field ligand only, right? So as in both the cases, the ligand which is coordinated to this metal center is weak field, so it is a high spin complex. Okay, both the complexes are high spin complexes. We know that this ml value, this is +2, +1, 0, -1 and -2. So here what is the L value? Orbital
3.
number 3, right? So if L is 0, it's S. If it's 1, it's P. If it's 2, it's D. And if it's 3, it's F. So for this D7 system, it will have F. Okay. Then what is the total spin number? That is S.
3 by 2.
S is half into total number of unpaired electrons. Half into number of unpaired electrons, which is there. In this case, we can see that there are 3 unpaired electrons. So half into 3, it's 3 by 2. And therefore, the spin multiplicity, which is 2s plus 1, will be 2 into 3 by 2 plus 1. that is equal to 4. So here it's 4F, right? So now, as we discussed here, that from group theory, for F, the irreducible representation for this term F, the irreducible representations will be A to G, T1G and T2G. So now, if we know the orgal diagram, then from orgal diagram for T1 F, for F as ground term, we will have T2G, T1G, F, and this one will be T1G, P. So from where this T1G, P is coming, this F is the ground state, but for every this F, we will get one excited state also, which will have this term P, and from there, this another T1G, this term is coming. Okay, and similarly here, we will write it T1GP. This is T1GF. It's T2G coming from F and A2G. Okay, so for this is very easy to remember, and we should remember this orgal diagram. So for tetrahedral D2 and D7 system, so for D n and D5 plus n, we get the same electronic transitions. So what orgal diagram says is basically what are the electronic transitions we are getting. Okay, so for Dn and D5 plus n, we will get the same, and for the whole of this, that is D10 minus n and Dn, they will have the opposite one. Okay, so if for this side we are getting for D2 and D7 tetrahedral, then this will be for D. The whole formalism of whole of this means this is D8 and D3 tetrahedral. Okay, for D3 and D8 tetrahedral, we will get this, and in for octahedral is just the reverse. Just the reverse means we can remember it like that. So it's D3 and D8 octahedral, and these transitions we will get for D2 and D7 octahedral. Okay, so by these transitions I am meaning trying to say that the transitions will be from A to G to T to G, A to G to, these will be the spin allowed transitions. Okay, A to G to T to G, A to G to T1G F, and A to G to T1G P. For this D2 D7 tetrahedral system and D3 D8 octahedral system, we will get these three spin allowed transitions, and for this D8 D3 tetrahedral system and D2 D7 octahedral system, we will get the transitions T1G F to T2G, T1G F to A2G, and T1G F to T1G P. Okay, so now in this case, okay, here I will write this is generating from F and this is coming from P. So here we know that both the systems are D7, where COH2O whole 6, this thing is an octahedral complex. This complex is an octahedral complex, whereas the COCl4 2 minus, this is a tetrahedral complex. So for D7 octahedral, this is for D7 octahedral. So the transitions are from T1G F to T2G, T1G F to A2G, and T1G F to T1G, P. Okay, so the ground state term for this octahedral complex is this T1GF, whereas for the D7 tetrahedral one, it will be this side, that is the ground state term here is A2G, and the transitions are from A2G to T2G, A2G to T1GF, and A2G to T1GP. So the ground state for the COCl1, COCl4 2 minus, it will be A2G. So among the given options, we can see that now we know that for COH2O whole 6 2 plus, which is an octahedral octahedral D7 system, the ground state term is T1G. Okay, and for COCl4 2 minus, that is D7 tetrahedral, the ground state term is A2G. Okay, now the next thing is that here we can see that in two options, sorry, first of all, it will not be A2G. Oh, sorry. Since it is tetrahedral, and tetrahedral complexes don't have center of symmetry. Okay, they are not centrosymmetric. So in this tetrahedral complexes, this G term, this will just get omitted. Okay, so if it's a tetrahedral complex, this G terms will not be there. So they are not centrosymmetric. So just T1 we will write, and this is T2. So here also we can write that for if it's octahedral complexes, then this G terms will be there. If it's not, then just they will vanish. Everything will remain the same. So here, okay, this is A2. Okay. So from this we know now that the option will be either T1G and A2. Okay. And next comes this number, like we have to know what is the spin multiplicity. So we already found out that for both the complexes it's a D7 system, and whether it's an octahedral or tetrahedral, like in octahedral it's T2G, it's split into T2G and EG, the degenerate d orbitals, they split into T2G and EG. D7 means 1 2 3 4 5 6 7, and for this is for octahedral system, and for tetrahedral system it will be 2 3 4 5, that sorry 1 2 3 4 5, that is E and T2. Okay, so 7 electrons we will fill here also, 1 2 3 4 5 6 and 7. So in both the cases the number of unpaired electrons is 3, is S will be 3 by 2 for both, and 2S plus 1 will be 4 for both, right? So 4 T1G and 4 A2 will be the correct option for this question. Okay, so is it clear?
Yes,
Yes.
ma'am.
uh, this orgel diagram, this is one thing, and for the other d orbitals also I will just draw. Yes. So for okay, this is for D1 and D6 tetrahedral, D1 D6 octahedral, this is D4 D9 tetrahedral, and this is D4 D9 octahedral. Okay. So in this one, I showed for D2 to D8 system. Okay, like not including D5 and D10. Why? Because they are completely, like, in those cases there will be no transitions. And for the other, that is from D1, D2, D3, D4, D6, D7, D8 and D9, we can understand that what are the transitions from these things only. So here it will be T, E and E. If it's an octahedral, then this G will come, or else it will not come. Okay. So orgal diagram is very important for knowing what are the transitions which takes place. So here the transition will be from this to this, and for these cases there will be one transition which will be this. So we can move on to the next question.
Yes, ma'am.
So the next question is question number 23. The question is the total number of valence electrons in W eta 3 Cp eta 5 Cp Co whole 2 is how much? The atomic number of tungsten is given. Okay, so it is W eta 3 Cp eta 5 Cp and 2 carbonyl ligands. So it is a very easy question. They have just asked that what is the total number of valence electrons. So tungsten is having how many electrons? How many valence electrons?
6.
Yeah, so it's a D5S1 system. We count it from neutral method. We will consider that 6 electrons from this, and Cp means this is a cyclopentadienyl ligand. Okay, and we know that cyclopentadienyl ligand is a ligand which can change its hapticity, right? So it can be eta 3, eta 5, eta 1. Okay, so if it's coordinating from only one of the carbons, like, then it will be eta 1. If it's coordinating from 3, that is, if it is coordinating with 3 only, then it's an eta 3. And if it is coordinating with all the 5 carbon, then it's eta 5. Okay, so depending on the hapticity, we can deduce that how many electrons it is giving. So 6 electrons are coming from tungsten. Eta 3 Cp means it is giving 3 electrons. Eta 5 Cp means it is giving 5 electrons. And carbonyl, they give 2 electrons each. So it is 6 plus 3 plus 5 plus 4. That is 18. So the number of valence electrons for this complex, this tungsten complex which is given in the question, is 18 electron. Okay, the answer is 18. It's clear, right? Okay, so we will move on to the next question. Question number 35 from 2018 paper only. The question is the O2 coordinated to metal ion centers in oxymyoglobin and oxyhemocyanin exists respectively as option number A, superoxide and peroxide, option number B, superoxide and superoxide, option number C, peroxide and peroxide, option number D, superoxide and oxygen. So first of all, oxygen, only oxygen means O2. Superoxide means it's O2 minus, and if it's peroxide, it is O2 2 minus. Okay. So they are asking that how it is coordinated in oxymyoglobin and oxyhemocyanin. So oxymyoglobin means, in myoglobin, you know that an iron is coordinated with 4 nitrogen from 4 histidine residues. And here also it is coordinated, and it is also coordinated to one of the histidine residue of the protein chain, and if O2 comes, then it will touch here. Okay, so here for oxyhemocyanin will be P2 2 minus or Fe3 O2 minus. So for oxymyoglobin, this oxygen O2, it is coordinated as O2 minus. Okay, this FeO, it is coordinated in a bent fashion, and it is FeO2 minus. And from where we know these facts? From the Raman stretching values. Okay, so there is a table from which we can understand, like there are this O2 will have different stretching frequencies for different coordination modes. Like if it is O2, it will have different stretching frequency. If it's O2 minus, if it's O2 2 minus, all of them will have different stretching frequencies. So from the stretching frequencies, it's been like proved that it is confirmed that it is present as an O2 minus in oxymyoglobin, and O2 minus means superoxide. Okay, and for the next case, that is oxyhemocyanin. So in oxyhemocyanin, we have first, what is the structure of hemocyanin where oxygen is not coordinated? There are 2 copper 1 centers, and each of them are coordinated to 3 histidine residues. Okay, yes. Okay, and when an oxygen is coming, O2 is coming, it will become like, okay, so these 3 N from the histidine residues will be there, and this O2 will coordinate in this fashion. So this is mu eta 2 type of mode of coordination of O2. And here this O2 is present as O2 2 minus. Okay, so O2 2 minus means it is a peroxide. So for oxyhemocyanin case, this O2 is present as O2 2 minus, that is it's a peroxide, whereas for oxymyoglobin, or it is present as O2 minus, that is superoxide. Therefore, for the given question, we know that oxymyoglobin, it is present as superoxide, and oxyhemocyanin is present as peroxide. So among the given questions, option number A is the correct option. It's clear? We should know the structure of this for knowing. Okay, so any other questions from this class? That thing I will read more on that and get back. Anything except that?
Ma'am, I have a doubt from organometallic chemistry from NPTEL videos, ma'am. Can I ask,
Yeah, ask.
ma'am? Can I? I have that screenshot. Can I share my screen?
Yeah, you can.
If you
Okay,
stop the
so
screen.
this thing, yeah, I'm stopping this, but yeah, this thing will be available online. So if you don't have any problem, you can share. Okay. Yeah, you can share. Hi, are you there? Hello, Pranay.
Now my screen is visible or not?
No, not yet.
Screen is visible or
No,
not?
is anybody else able to see that because I can't see?
No, ma'am.
Now it's visible or not?
No.
I'm sorry, ma'am. We could
Okay,
discuss in the
Pranay, you
next.
can share. Yeah, we can discuss on next day. But before
Yes.
that, you can also send me in this my mail ID. Okay.
Yes, ma'am. Yes, ma'am.
So
Yes,
I
ma'am.
will just go through it. If I am not aware with that, I will see and I will give the answer.
Okay. Thank you, ma'am. Thank you, ma'am.
Yeah. So, okay, then that's all for today's class. Anyone else having any question? It's clear.
No, ma'am. Thank you.
Yeah. Okay. Thank you.